In this third lecture, we will explore the bialgebra structure of Feynman diagrams and Feynman integrals, corresponding to the bialgebra we've seen on multiple polylogs. So let's focus on a concrete example. Let's just take a scalar bubble integral, and let's take one that has one massive propagator and one massless propagator. So I'm indicating the massive one by a thick line, a massless one by a thin line, and then we have external momenta. So the kinematic invariance, the scales involved here are m squared for the massive propagator and a p squared for the external momentum. Now, if we evaluate this in dimensional regularization, we'll find it has an epsilon expansion given in terms of multiple polylogs. Instead of choosing the usual 4 minus 2 epsilon dimensions, let's evaluate it in 2 minus 2 epsilon dimensions. Now, these kinds of shifts to other even dimensions or regularizations around other even dimensions do come up very naturally in computing Feynman integrals using techniques of dimensional recurrence and reduction that can give you different powers of propagators. So in fact, this function is very closely related to the function we would get if we evaluated it in 4 minus 2 epsilon dimensions. But it has the advantage that in 2 minus 2 epsilon dimensions, the result will have uniform transcendental weight. And that's a nice property to work with. So in the Laurent series expansion in epsilon, that means that as we go to the successive order in epsilon, the coefficient of the next power of epsilon will have its transcendental weight also increased by epsilon. So to be able to say that the full expression is of uniform weight, we formally assign epsilon itself, this dim-reg parameter, to have weight minus 1. And that way every term has exactly the same transcendental weight. Now, furthermore, it has an additional nice property that not only does each term in this series expansion have the same weight, but if we normalize it, the whole integral, by what's called its leading singularity, in this case, it suffices to know that this is a function 1 over p squared minus m squared, some rational or algebraic function of the kinematic invariance in general. Then, furthermore, it will be not only uniform transcendental weight, but it will also be pure. Intuitively, that means that we really just have logarithms or dilogarithms and or polylogarithms in general, and sort of this same algebraic factor has been removed from each term. That means it's common across all the terms in the expansion. It's possible to see that this is true going back to the integral expression of this Feynman integral and seeing what it is in epsilon and sort of performing the power series under the integral sign, although one has to take care with the divergences, which of course is the reason that we're introducing epsilon. So after doing this, we select dimensionality, we select a normalization, knowing something about what we're going to find. And so now, suppose we compute this integral order by order in epsilon. So we start with producing the result of the Laurent expansion. And if we do that, we find that we get a leading term of minus 1 over 2 epsilon. So this is the reason we have to introduce dimensional regularization. This is a divergent integral, not a finite integral. This is an infrared divergence. Then the next term will be constant in epsilon, and this is log m squared minus p squared squared over m squared. And we could go on, actually let's just leave it at that for this simple example. Then you would get the order epsilon term, for example, would have a coefficient of transcendental weight 2. Now let's compute the coproduct on this expansion. Again, order by order in epsilon. And we'll find, just using what we learned last time, that the coproduct of this expression is, again, we do this order by order. So the first one has no logarithms. This is really just, we treat it as a rational number. Epsilon comes along as a constant. And then at the constant order, now we have a log. So we also know what its coaction will be. It's log tensor 1 plus 1 tensor log of this same argument. Minus one tensor log plus order epsilon. Fine, and we could go to as many orders of epsilon as we like, or as we're able to. And now what we're going to explore is the idea that this expression, this coaction acting on the Feynman integral in its evaluated form, can be re-expressed in terms of Feynman integrals. So we'll see this actually turns out to reproduce a set of Feynman diagrams on the right-hand side. That is to say, this coproduct, and this will hold to arbitrary orders in epsilon, that we can package up what we find on the right-hand side in terms of other evaluated Feynman integrals. So we start with the same one here. Let me just write down what will turn out to be true. So I have the same integral. And then we have a term with a tadpole tensor, a sum of, again, the same integral. I'm going to have to add some things into this formula, which you'll see in a moment. Which are extremely important, which are cut lines. So this is not exactly the same integral. Here, I'm decorating some of the propagators with cuts. This cut line on a propagator means that when you're applying the Feynman rules, there's a special rule that we apply to these lines, which is that the propagators are constrained to be on shell, on their mass shell. So cuts constrain propagators to their mass shell. And these are often imposed, these constraints are often imposed by replacing the propagators by delta functions, imposing the on-shell conditions in integrands. But I prefer and find it's more useful to think of an alternative formulation, which is to define them as residues of the integral at the singularities given by the on-shell conditions. In complex analysis, these are equivalent operations, but once you think about residues, it lends itself much better to generalizations and to manipulations of integrals of the kind that we'll be interested in. So now we have on our, well, I've just shown and haven't even checked it yet in this one example, but we're going to lead into the idea of a coaction and therefore a bialgebra structure on Feynman integrals and their diagrams. We've leapt it right ahead to the coaction. Let me just comment on ordinary multiplication. So ordinary multiplication of Feynman integrals will just be just the product of integrals or products of diagrams, so just write them next to each other, which could represent a scattering process. But actually, this is not unknown, right? If you stick together, for example, two one-loop integrals and you just stick them together at one of their vertices, this kind of Feynman integral does come up very naturally in reduction of higher loop Feynman integrals, and it is exactly the product, of course, of the lower loop Feynman integrals. So that's built in as well. The idea of this kind of coaction, as mentioned in the first lecture, that applies to Feynman integrals was predicted by Brown, and it inspired the work I'm going to outline here. But this is work I've done with Samuel Abreu, Claude Dürr, and Enan Gardi. We found that making this idea really concrete really demanded working in dimensional regularization, because as you introduce the cuts, well, first let me say, if you want to formulate this and express the coaction of a Feynman integral in terms of other Feynman integrals, you will be led into cut integrals, like it or not. You can't formulate this kind of coaction purely in terms of uncut integrals if you want it to agree with a series expansion. Moreover, even if you start with a finite integral here on the left-hand side, which we didn't in this case, but if you did, you would find that these kinds of integrals that are related, whether they have fewer propagators or additional cut lines, can introduce divergences, and so you need to introduce a regularization that will allow them to cancel, and we find that dimensional regularization works really well. Let me also, while we're here, mention, right, we gave this propagator a mass. This tadpole here is not just any old tadpole, that has specifically the same mass. And also when we introduce cut lines here, we're really keeping the same mass on the massive propagator throughout. In a way, all these diagrams will have labels. So let me just show what this right-hand side is going to look like in terms of its multiple polylog expansion. So I'm not yet deriving it here, but let me just give you the answers and you can think about how you might check them. So this here is the double cut of the bubble. This in its first few orders in the epsilon expansion, this will be 1. This is not divergent, plus epsilon log p squared over p squared minus m squared squared plus order epsilon squared. Actually, you'll see why we need to go to the next order, to order epsilon, in order to check this properly. Then, so I've written the uncut bubble. We have the tadpole. So again, now, when I wrote down the original diagram, I specified it was in a certain number of dimensions and that it was normalized, and the same is true of all these other expressions I'm going to write down. They're evaluated specifically in 2 minus 2 epsilon dimensions here and normalized by their leading singularity, some factor that's common to all the terms, their epsilon expansion. So then this one we'll find can be written as minus 1 over epsilon plus log m squared. Right, this one can only depend on m squared because there is no p that's identifiable in the tadpole. And then finally we have one more, this integral where we've only cut one propagator. And if we evaluate it, we find we have minus 1/2 plus epsilon over 2 log m squared p squared minus m squared squared over p squared squared plus order epsilon squared. So let's see if we can check this relation, this in evaluated order by order in epsilon. So our first check formula, it will have to be at order epsilon to the minus 1, because that does appear on the left-hand side. Now on the right-hand side, we do get divergences from these first entries here, and all the cuts, however, are finite. So this is pretty easy to check. We only need to collect the leading order terms. So we'd find that we have minus 1 over 2 epsilon, 1 tensor 1 on the left-hand side. And on the right-hand side, we are taking this same expression times 1, so nothing from this term here, and then we'll have this divergence from this term and then a sum of other terms here. But notice in this sum, the leading order, right, we have minus 1/2 here, and here we have plus 1/2 times 1. So these combine to give 0. So we're not picking up any extra divergence from this term. So in fact, if I restore the sign that I just omitted to write down, we have already verified the leading order of the coaction formula. Now let's check at subleading order. Epsilon to the 0. So now, here in the first term, we're looking to combine this expression on the left of the tensor product with this on the right, and we're looking for order epsilon to the 0. So we'll have one contribution from the pole term in epsilon times epsilon, and this will give something like a constant tensor log. And then we'll also have the tensor product of these constants. So this will be a log tensor constant. We have exactly these two terms, and if we write them down, so right-hand side term 1 is 1/2 log m squared minus p squared squared over m squared tensor 1 minus 1/2 times 1 tensor log p squared over p squared minus m squared squared. Now in the second term, really the second pair of terms, now from the tadpole we get this, a divergent term, constant term, and then from the cuts, now the cuts don't have any 1 over epsilon pole, and remember in the previous step we already saw that their leading terms combine to give 0. So really in this combination starts at order epsilon. So we only have to take this combination on the right of the tensor product, and then on the left, only the divergent term here will contribute to the overall coaction at order epsilon to the 0. Right? So it's minus 1 over epsilon, tensor this sum. So collecting all those terms, we have minus 1 over epsilon, tensor epsilon, and then inside the sum we have 1/2 log p squared over p squared minus m squared squared plus 1/2 log m squared p squared minus m squared squared over p squared squared. And we can simplify this here. We see that there's some cancellation with these factors entirely and with these factors partially. So this all simplifies to, we can also cancel the epsilons, minus 1/2, 1 tensor log m squared over p squared. Then when we combine this second term with the result of the first term, we find, of course, we're looking to combine this term with this term where we have the log on the right side of the tensor product. And then again, there's a bit of cancellation, and we'll find that we get exactly the same argument of the log here as here in these two terms, using the minus sign also to invert the argument of the logarithm, and we recover exactly what we wanted on the left-hand side. So that completes that check. Now let's have a look at the structure of this formula, coaction formula, in terms of diagrams. Notice that our check was quite a non-trivial one. There was quite some interplay between the various terms on the right-hand side, even from neighboring terms in the Laurent series expansion. So it is not that the multiple polylog expansion immediately gives you this result. In fact, you could argue that putting it in terms of diagrams has made things more complicated in terms of the functions we've seen here. But the idea is that this kind of coaction expansion can give us some physical insight and some clues into how to construct coactions of Feynman integrals, perhaps even before we can compute them. So let's have a look at what's happening here. Here in the coaction expansion, we find that in the first entry, so the left of the tensor product, we have the original integral or the integrals that you could obtain from it by contracting some of the propagators. So you could contract this massless propagator to arrive at this tadpole. You could also imagine contracting the massive propagator, but then you get zero, because one of the properties of the dimensional regularization scheme is that if you have a loop that consists only of a massless propagator, that is just set identically to zero in dimreg. So other than that, everything is present. Now on the right entry, in the right entry of the coaction, as mentioned, we do have cuts, but these are also quite specific cuts. So the rule or the principle we observe here and we'll be looking for is that when a propagator is still present on the left because it has not been contracted, then that one will be cut on the corresponding right entry. So here we have one uncontracted propagator and it is cut here. It is also cut in the other term, and an additional propagator has been cut. And this term with a factor of 1/2 sort of goes along with this, which is why it's been placed in brackets in a sense that we'll see shortly. We can call this a deformation term, and it's related to singularities at infinity in the loop integral. If we disregard the deformation term for just a moment, we would find that what we see here in this operation on graphs is a kind of incidence algebra. Again, we're selecting a subset of the edges to contract or to be uncontracted, and then selecting that same subset in some sense on the corresponding right entry. And that's essentially the idea why this is a valid coaction and how you could argue that this kind of diagrammatic operation, in fact, it does respect the coassociativity, which is an important check of any putative coaction. Let's go step back for a moment and see how this works in an even simpler example, namely just the tadpole integral itself. So this one. In fact, let me give its exact expression because it is easy enough to compute directly. And from here you can see that as you go to higher orders in the epsilon expansion, you'll just get powers of logs. Now the cut tadpole is also pretty easy to compute. So this is actually very similar. It's also just a power of m squared, or actually, well, minus m squared, and the minus m squared in the argument, that just has to do with how we routinely think about computing cut integrals. Now, let's predict the form of the coaction. So that will be, if we take the coaction of the uncut tadpole, we will get, just thinking about contracting propagators, there is nothing to contract, right? If you contract this propagator, then there's nothing left in the integral. So this is the only thing that can appear on the left. So we have at most one term. And then on the right, since that propagator is still present, then it's got to be cut. And this is true. And you can verify it using these expressions here to any order in epsilon. Moreover, what's also true is that you can apply cuts to these equations. So if we're saying we can understand the coaction purely as an operation on these diagrams, even before evaluating them, then we can just take the diagrammatic operation and apply it to a cut tadpole directly. And this is true as well. Now, a cut propagator, when it appears on the left, if it's present, then it's cut on the right. Now, it was already cut, so it's just still cut. And this is not surprising since, again, you see these are really essentially the same function, and it's easy to check that if you just take powers of logs, you get, and take the coaction, you get, of course, the same corresponding powers of logs. We saw this in the last lecture. And so it's really just checking that the prefactors work out correctly. We've normalized them so that it's convenient, and that does work out. Let me also note once again, everything here is evaluated in 2 minus 2 epsilon dimensions. So we can apply these same rules to all kinds of one-loop Feynman diagrams. A diagram now with one-loop diagram with n propagators will be evaluated and propagators in 2 ceiling n over 2 minus 2 epsilon dimensions. It turns out that this is the dimensionality that will give uniform transcendental weight. And moreover, this set of one-loop integrals, as you vary n over all the positive integers, suffice to form a basis of all one-loop integrals. Let me also comment on this change of argument, say in the logs and the expansion. Now, it looks, of course, on the surface different. Here we're expanding in log of m squared, and here we're expanding in log of minus m squared. But notice, in particular, for this coaction formula, the cut part is only appearing in the right entry of the coaction. And do you remember from last time when we discussed the coaction on multiple polylogs and why it's a coaction and not a coproduct, that in the right entry we are working in a Hopf algebra, which is the multiple polylogs modulo I pi. So the difference, of course, between this log and this log is precisely proportional to I pi. And so those differences just disappear when we take this coaction. That means, more generally, that we don't need to be very particular about which region we're evaluating the cut integrals in. And this is a big help in defining cut integrals precisely, to know that when you set up a definition rigorously, you're only going to be using them, in this context, modulo I pi. And that could be true physically as well. This has a clear definition in terms of a scattering process, but by the time you take a cut, you might be considering some kind of discontinuity across a singularity of the integral, and discontinuities can be taken in different directions and at different locations. So it does make sense to be losing that bit of information. So let's go on to a bigger example, which is a general bubble. So one with generic masses on both propagators. And let's label these propagators 1 and 2, so we can keep track of the different masses. And we'll evaluate its coaction, first of all, in terms of diagrams. So in terms of diagrams, we'll predict the same kind of structure we saw earlier. So we'll have one here, some integrals that will come along with cuts shortly. This is going to become a formula, and I also need some tadpoles that come from contracting either of the propagators. So we predict we'll have such a term, this kind of linear combination with different numbers of cuts. Okay, so first of all, for the first terms, if a propagator is present on the left, then it is cut on the right. Present, let's give these labels. So let's say we've contracted away propagator 2 here and contracted away propagator 1 there. So 1 is still present, so 1 is being cut here, and then we have an extra deformation term with both propagators cut. And the same thing here. And so let's just insert plus 1/2 and plus 1/2. This is what we predict, and in fact we can verify this for the generic bubble with masses. And so you see, if we take a limit in which, say, propagator 2 becomes massless, then we recover the example we had before, and everything is the same. This is the same. We can take the limit on the right-hand side as well, except that this tadpole will be set to 0. So we're just missing the bottom line, and that's exactly what we did write down and verified earlier. As we discussed in the tadpole example, you can also apply this to a cut of a bubble. So imagine if you cut propagator 1, then you just do the same procedure where 1 is cut. So here it would be cut, here it's already cut and it's still cut. In this term we would cut propagator 1 and still have both those terms here. By the time we get to this term though, however, it's important to note that this tadpole is derived as a contraction. And if you contract a propagator that's already cut, then it doesn't just disappear like this, it actually becomes 0. So this bottom line would again be missing in the case where propagator 1 is being cut. So we don't get a 3/2 term here, we get 0. So propagators that are both cut and contracted set their entire diagram to 0. Now, we can predict now exactly how these deformation terms arise, and to explain that, let me write this a bit more formally, rather than in terms of pictures, in terms of integrals. So let's write the bubble, general bubble, just very schematically as an integral over of an integrand, which I label just omega 1, 2 to show that it has propagators 1 and 2. I mean, we know what it is explicitly, but let's abbreviate it like that. And let's call our original integration contour gamma sub empty set, because remember we're going to define these cut integrals by a change of contour that encircle the singularities of the propagator. So those are going to be like gamma sub 1, gamma sub 2, gamma sub 1, 2, and here nothing is being cut, so we are just starting with gamma empty set. Now this equation for the coaction, written in terms of integrals, I'll just convert each diagram here to this schematic integral form. So we have integral over gamma empty set omega 1, 2 tensor. Now it's cut, so we denote that gamma 1, 2, the same integrand. Now in the second line, we have, in the beginning, one of the propagators has been contracted, so we have only omega sub 1. That's uncut. And then inside the brackets, we have now integral with one propagator cut, propagator number 1 cut, so is omega 1, 2 integrated over gamma 1, 2. Okay, plus 1/2 times omega 1, 2 with both propagators cut. And then the same thing with 1 and 2 exchanged as propagators. It's gamma 2, omega 1, 2 plus 1/2 gamma 1, 2, omega 1, 2. Okay, now let's combine these terms a bit. When we notice that here these terms are related inside the square brackets by having the same integrand but different contours. So let's just define a new contour. Let's define this linear combination of contours, because contours, integration contours, can be combined in linear combinations perfectly analogously to doing similar operations on integrands. So let's call this small gamma 1 is big gamma 1 plus 1/2 gamma 1, 2. Similarly for small gamma 2. And then just for completeness, let's also have gamma 1, 2 equals big, small gamma 1, 2 equals big gamma 1, 2, which will replace this one here. So this brings the full coaction into a really uniform expression where we have pairs of integrands and contours that go together. So this now is really the structure of the coaction, and in fact general coactions on integrals. So what we refer to as a master formula for coactions on integrals would be this kind of expression where you have coaction of some integral, so some integrand omega integrated over some contour gamma, and we're just inserting a complete set of dual integrands and contours. So in the first entry, you change the integrand as you run over this full basis of some kind of integrand. Then the second entry, each term comes along with its corresponding contour and the original integrand. So the original integrand and contour are still present respectively in the second and first entry, and then they are paired now with integrands and contours running over some kind of basis. You can also check that this satisfies co-associativity, and if you can identify something discrete about how you're changing this basis, then it has very much the flavor of the incidence algebra that we've seen. Now, coming back to the specific case of one loop integrals, as seen here, we can predict, based on the geometry of one loop as an integration variable, that these dual contours that we want to select are in fact related to contours picking up surrounding the pole at infinity. So the rule is, and this can be shown, that if you have an odd number of propagators being cut, so just like one propagator here, then you must also additionally include the pole at infinity to define the dual contour small gamma. There's this factor of -1/2, which can also be explained. And the rule is as well that if you have an even number of propagators, so an even number of cut propagators, that then you do not pick up the pole at infinity. So this is, of course, just itself, only the contour encircling those two or even number of visible propagators. And this is a pattern that continues to arbitrary one-loop integrals when evaluated in the correct number of dimensions. So this master formula for coactions has an interpretation in terms of multiple polylogarithms. This you can choose omegas and gammas that will make this formula look like the coaction on multiple polylogs in terms of the g's or i's that we saw in the previous lecture. It also has an interpretation that we've seen now in terms of Feynman integrals that corresponds to a really graphical operation on the propagators and their cuts. And let me just say clearly, we understand this quite well in the one loop case. Beyond one loop, it is more speculative, but there are some examples of how this pattern continues to hold. And it remains to be seen whether this can be really well established, because of course the geometry gets quite a bit more complicated beyond one loop. And we'll see in the following lecture an interpretation in terms of the closed forms of Feynman integrals that corresponds to both of these. So again, I want to emphasize that the diagrammatic operations really correspond to the same coaction that we derived for multiple polylogs, so it can be checked in the case where there is such an expansion. And there is a multiple polylog expansion for all one loop Feynman integrals. That will not be the case generally beyond one loop, where we might need to introduce more complicated types of functions. But now to close this lecture, I just want to comment again. We've seen that coactions and this kind of formula really lend itself to taking discontinuities and differential operators. I mentioned this in the last lecture, because discontinuities act only on the first entry, and differential operators act on the second entry. And this can be traced to the fact that discontinuities involve changing the integration contour, which is inherited here in the first entry, and differential operators act on the integrand, which is carried over here in the second entry. Looking at an example such as this one, you'd see if you, for example, consider a discontinuity across the full diagram. So this is in a momentum channel. The discontinuity acting on, so discontinuity with respect to p squared would act on each of these first entries. Now, there is no p squared remaining in these contracted tadpoles, so discontinuity here would become 0, and we're only left with this term, where we find the discontinuity of this integral is the discontinuity of, well, itself essentially times its cut. Now this example is really too small to appreciate that, but if you looked at larger examples, you would see that if you take a discontinuity in a given momentum channel, you would collect the diagrams at weight 1 in the expansion that correspond exactly to these kinds of traditional cuts in that same momentum channel. And likewise, if you apply differential operators to this integral and then carry through the coproduct, you find they'll act on the cuts. And again, if you take the Laurent expansion and just focus on the terms of low weight here, those will correspond to nearly maximal cuts, and you can derive differential equations with just a little bit of information about the nearly maximal cuts. And then the terms in the differential equations will have all these terms that come along in the first entry. Consequently, it also gives you some information about the symbol alphabet that can arise in these integrals. So I'll close really with this master formula and say that in the next lecture, we'll see this in yet a third form that is compatible with the two that we've shown thus far.